Hello and welcome to the PySpark course. I'm going to add chapters to this course, so if you want to skip some lectures or re-listen some of them, you can find the timestamps easily from the description of the video. I created a pretty easy data for this course for you to learn the concepts better and easier. Also, I'm going to show data creation codes in every lecture so you can get used to the syntax of the PySpark. Now we can start. PySpark is a Python library built on top of Apache Spark, an open source distributed computing framework. It allows us to process vast amounts of data in parallel across a cluster of machines. This makes PySpark an ideal choice for big data applications where traditional data processing tools may fall short due to scalability issues. Let's talk about some advantages of PySpark. One of the key advantages of PySpark is its ability to perform distributed computing. Instead of relying on a single machine, PySpark distributes data across a cluster, allowing us to process large datasets efficiently. This parallel processing significantly reduces the computation time. PySpark stores data in memory, which means that the intermediate results can be cached and reused across multiple computations. This in-memory processing minimizes the need to read data from disk repeatedly, leading to faster data access and manipulation. Also, PySpark provides extensive APIs and libraries for data manipulation, machine learning, graph processing, and more. It integrates seamlessly with other Python libraries like Pandas and NumPy, enabling data scientists to leverage familiar tools. Let's consider an example use case where we need to analyze customer data from a massive e-commerce platform. Traditional data processing techniques might struggle to handle the huge volumes of data, but PySpark comes to the rescue. We can easily distribute the data across multiple nodes in the cluster and process it simultaneously, making our analysis lightning fast. Now we will get our hands dirty and set up our development environment to start our PySpark journey. We will be using VS Code as our code editor and install PySpark to leverage its powerful capabilities for big data processing. First, let's install VS Code if you haven't done so already. VS Code is a lightweight, feature-rich code editor that supports Python development and integrates seamlessly with PySpark. For installing it, you can open your web browser and navigate to this site, code.visualstudio.com. Then you need to click on the download button to download the VS Code installer for your operating system. Once the download is complete, run the installer and follow the on-screen instructions to install VS Code. Next, we need to ensure that Python is installed on our system. If you already have Python installed, you can skip this step. Otherwise, follow these steps to set up Python. You need to open your web browser and navigate to this site, python.org. And then you need to download the latest stable version of Python for your operating system. Run the installer and make sure to check the bugs at Python to path during the installation. With Python in place, we can now install PySpark. PySpark requires both Java and Apache Spark to be installed. But don't worry, the installation process is straightforward. You can open your terminal from here. And you need to write pip install PySpark, but I'm going to write pip3 since I'm going to run this on Python 3 and it's going to be installed in this way. After this downloading process finished, we can use PySpark. We just installed PySpark. Now we will dive into two fundamental components of PySpark, SparkContext and SparkSession. These components play a crucial role in enabling distributed data processing and providing a high-level API for interacting with data. Let's start with SparkContext. SparkContext is the entry point to any Spark functionality. It represents the connection to a Spark cluster and serves as the client-side driver program. SparkContext enables your application to access Spark's distributed computation capabilities. For this, we are going to say from PySpark, which is we just installed, import Spark context, and we are going to run this and we are going to say Spark context is going to be equal to the Spark context. We are going to say local and PySpark, let's say intro, and we are going to run this. In the code, we import the SparkContext class from the PySpark module. Then we create a Spark context named PySpark intro with the master URL set to local, indicating that we are running Spark in local mode for development and testing. Next, let's explore SparkSession, a more recent addition to PySpark that provides a single entry point to interact with various Spark functionalities. It includes the features of both Spark context and SQL context, making it the recommended way to work with PySpark. For that, we are going to say from PySpark.sql import SparkSession, and we are going to run this, and we are going to say Spark is going to be equal to the SparkSession.builder.app name, and let's say PySpark intro, and we are going to say get or create, and we are going to run like this. In this code, we import the SparkSession class from the PySpark.sql module. We use the SparkSession builder to configure the session and set the application name to PySpark intro. The get or create method ensures that if a Spark session already exists, it will be reused, otherwise a new Spark session will be created. Now let's briefly discuss the use cases for Spark context and Spark session. We will firstly talk about Spark context. Use Spark context when you need fine-grained control over Spark configurations and lower-level RDD, which means resilient distributed dataset operations. However, for most high-level data processing tasks, we will rely on Spark Session. Now we are going to talk about Spark Session. Spark Session simplifies the process of working with structured data by providing a DataFrame and Dataset API. It's a recommended entry point for most PySpark applications, especially for data scientists working with structured data and machine learning tasks. Now we will explore one of the foundational concepts of PySpark, RDDs. RDD means Resilient Distributed Dataset, and from now on I'm going to say RDD for that. RDDs form the core of Spark's distributed data processing capabilities, enabling us to work with large datasets efficiently. We will also delve into RDD transformations and actions, which are essential for processing data in a distributed manner. RDDs are immutable, distributed collections of data elements that can be processed in parallel across a cluster of machines. They are fault-tolerant, meaning if any partition of an RDD is lost, Spark can recreate it automatically using lineage information. Let's create a RDD from a list. We are going to say data is going to be equal to the 1, 2, 3, 4, and 5. And we are going to say RDD is going to be equal to the, remember it, we used it like S and C parallelize. We are going to say and we are going to pass data like this. In the code, we create a RDD called RDD from a Python list data using the parallelize method. Now we are going to talk about RDD transformations. Are operations that create a new RDD from existing one. Transformations are lazy, meaning they are not executed immediately, but their execution plan is recorded. Some common RDD transformations include map, filter, flat map, and reduce by key. Let's say squared RDD is going to be equal to RDD.map, which we just said. We are going to say lambda x is going to be x and 2, like this. We just mapped each element to its square. Now let's do something similar. Even RDD is going to be equal to the RDD.filter. Lambda is going to be, and we are going to say 0, like this. We filtered even elements. In the code example, we use the map transformation to create a new RDD, squared RDD, where each element of the original RDD is squared. We also use the filter transformation to create a new RDD, even RDD, containing only the even elements from the original RDD. Now we are going to talk about RDD actions. RDD actions are operations that trigger the execution of transformations and return results to the driver program or write data to external storage. Actions are eagerly evaluated and initiate the computation on the RDD. Some common RDD actions include collect, count, reduce, and save as text file. Let's use collect and count. For this, we are going to say collected data is going to be equal to the squared RDD collect. I made a typo there. Squared RDD dot collect, and we are going to run like this. We can use this for collecting all elements to the driver program. I'm going to scroll down a little bit, and we are going to say number of elements is going to be equal to the squared RDD dot count, and we are going to run like this. We can use it for counting the number of elements in the RDD. In the code, we use collect action to retrieve all elements from the squared RDD and bring them back to the driver program as a Python list. We also use the count action to determine the total number of elements in the squared RDD. Now we will dive into the DataFrame and Dataset APIs, powerful abstractions built on top of RDDs that enable us to perform data manipulation and analysis with ease. Let's just get this smaller like this. These APIs provide a higher level, more structured way to work with data, making data science tasks in PySpark more intuitive and efficient. Let's firstly talk about the Dataset API. Dataset API combines the benefits of both DataFrame and RDD APIs. It provides a type-safe, object-oriented programming interface with the performance optimizations of DataFrame API. Datasets are available in both Python and Scala and allow you to work with strongly typed data. Let's import from PySpark.sql.types. We are going to import struct type, struct field, string type, and integer type. We are going to create a schema for the data set. We are going to say struct type, and we are going to open a list like this, and we are going to say struct field, and let's create a data set with name, and we are going to say string type like this, and we are going to say true here. Now we are going to do struct field, and we are going to say age integer type, and this one is going to be true like this. And let's create another one as struct field, let's say salary. It's going to be integer type also, and it's going to be like true, like the similar with the last one. Let's run our schema here, and we are going to insert some data to here. Let's create a data set like data is going to be equal to the Alice 28, and let's say 45,000 for its salary, and we need parentheses for this. Like we are going to add one here, and we are going to add one here, and let's create another entry as Bob. Let's say 36 for its age and 60,000 for the salary, and let's create another one as Kathy. Let's make this last one 23 and 35,000, let's say. And now we are going to say ds spark create data frame with data and schema we have. We are going to run this, and we are going to say ds is going to be equal to the ds.alias, and let's say employees here. Let's see the dataset we created. Like we are going to say ds.show, and we are going to run like this. In this code example, we define a schema using the struct type and struct field classes to specify the column names and data types. Then we create dataset ds from a list of tuples, with each tuple representing a row of data. We use the as method to give the dataset an alias employee. Now we are going to talk about DataFrame API. DataFrame is a distributed collection of data organized into named columns. It is conceptually equivalent to a table in a relational database or a spreadsheet with rows and columns. DataFrame API in PySpark provides a more natural and efficient way to handle structured data compared to RDDs. For using this, we can say data file and we can set our data CSV file like path to data.csv, and we are going to use like df spark. We are going to use the read CSV like this, read CSV, and we're going to pass data file headers if data had headers, and we are going to say here infer schema is going to be true, and in this way we can make Spark read our CSV files. In the code example, we create a DataFrame df by reading data from a CSV file using the read CSV method. The header true option indicates that the first row of the CSV file contains the column names, and the infer schema true option instructs Spark to automatically infer the data types of each column. Normally, I was thinking to add some CSV files JSON data for this course, but I'm not going to add any external dataset since I want to keep it simple as possible for you to understand, and I'm also going to show related codes and you can easily apply these codes to your dataset with the way I show. Now we are going to explore working with both structured and semi-structured data in PySpark. We will leverage the dataset we created in the previous lectures to demonstrate various techniques for handling different data formats. Here's the dataset codes we used. We are going to add parentheses here and we are going to run this for seeing our data once again. We are going to use this. Structured data refers to data that can be organized in a tabular format with rows and columns. We have been using structured data in the form of data frames and datasets. In the code example, we create a DataFrame df using Spark create data frame, specifying the dataset and column names. This represents structured data, and we can easily work with using DataFrame operations as we have seen in previous lectures. Now we are going to talk about semi-structured data. Semi-structured data doesn't have a fixed schema like structured data. Instead, it has a flexible structure that can include nested data and arrays. JSON and XML are common examples of semi-structured data. I'm going to show you the necessary code for reading them, but I'm not going to do any other operations. I will just show the code for working with them. Once again, I'm trying to keep it simple, and we are going to say JSON data file. We are going to save our JSON file like this, path to data.json, and we are going to say df json is going to be equal to the spark.readJSON, and we are going to say JSON data file just like this. You can use semi-structured JSON data and you can read it into a data frame using Spark read JSON. PySpark infers the schema based on the JSON structure. Semi-structured data is valuable for handling complex and nested data formats. Let me also show you the XML format. For that, we are going to say XML data file, and we are going to say path to data.xml, and for using it like the way we want it, we are going to say df xml is going to be equal to the spark.read.format, and we are going to say xml here, and we are going to use option row tag, and we are going to set our row tag here like employee, let's say, and we are going to use load XML data file here, and this is the code for reading XML file into a data frame. In this example, we are reading semi-structured XML data into a data frame using the XML format. Now we will discuss data cleaning and preprocessing techniques using PySpark. Data cleaning is a crucial step in the data science pipeline as it ensures that data is accurate, consistent, and ready for analysis. We will be working with the dataset we created in the previous lectures to demonstrate various techniques for cleaning and preparing data. One of the common data cleaning tasks is dealing with missing values. Missing values can cause issues during analysis, so it's essential to address them appropriately. So let's recreate our data with missing values, and we are going to use filling methods on that data. Let's say data with missing, and we are going to say Alice 28 45,000 again, and let's create Bob, and let's create a non-value here, missing value, and enter salary, and let's create Kathy. This time we are going to leave salary side empty, and I think we are good to go with this. Let's run this, and we are going to say df missing is going to be equal to the Spark create DataFrame data with missing, and we are going to say name, age, and salary. Let's fill missing values in age column with mean of that column. For this, we are going to say mean age is equals to the df missing dot select. We are going to use age, and we are going to say aggregate, and we are going to open a parenthesis, and we are going to say age and average, and we are going to use collect with this. Also, we are going to add one more here, and when we run this, we are good to go. Now we need to imply it, so we are going to say df cleaned is equals to the df missing na.fill, and mean age and subset is going to be age. Now when we check df cleaned with show, we are going to see cleaned. We are going to see that the age column is filled with the mean value of it. In this code example, we create a data frame df missing from the dataset that contains missing values. We use the na.fill method to replace the missing values with the mean age and mean salary calculated from the non-missing values. Feature scaling is another crucial step in data preprocessing, and now we are going to talk about it. It standardizes the range of independent variables, ensuring they have similar scales. Common methods include min-max scaling and standardization, which we can also refer as z-score scaling. We are going to import the necessary modules like from PySpark.ml feature, import min-max scaler and standard scaler, and from again PySpark ML feature we are going to import vector assembler. Let's create the data frame once again with the original data set we have. To remind you, we are going to use create data frame data, and we are going to say here name, age, and salary. Let's start by feature scaling. For this, we are going to say assembler is going to be equal to the vector assembler input columns is going to be equal to the age and salary, and we are going to say output column is going to be features, and we need to do a transformation here like data for scaling, and we are going to say assembler that transform, and we are going to pass our data frame inside of it. And let me show you the version. It became now like this, and we are going to see a new column as features in here. Let's do min-max scaling. For this, we are going to say scalar min-max is going to be equal to the min-max scalar. Once again, we are going to say input column is going to be equal to the features, and output column is going to be equal to the scaled features. And we are going to run this. We are going to say scaled min-max is going to be equal to the scalar min max. This time we are going to use fit, first the data for scaling, and then we are going to use transform data for scaling. And let's also run this and check how it looks. Scaled min max dot show. We are going to see the scaled features here. Now let me show you the standardization, which we can also call as z-score scaling. For this we are going to say scalar standardization is going to be equal to the standard scalar, and input column is going to be equal to the features, and output column is going to be equal to the scaled features. I made a typo there. I'm quickly going to fix this, like I'm just going to capitalize this and run the cell. Now let's also add some stuff to here, like let's say with standard deviation is going to be true and with mean is going to be equal to true. Let's run like this. And now we are going to say scaled standardization is going to be equal to the scalar standardization dot fit data for scaling, and we are going to use transform also, of course. I made a typo there, transform and data for scaling again. And we are going to run like this. Now let me show you the final version of our data frame, scaled standardization.show, and it is the final version of our scaled features. In this code example, we demonstrate both min-max scaling and standardization. We first use a vector assembler to combine the age and salary columns into a single feature vector. Then we apply min-max scaler and standard scaler to scale the features. That was all for the data cleaning and pre-processing lecture. Now we will explore how to perform exploratory data analysis using PySpark. Exploratory data analysis is a crucial step in the data science pipeline that allows us to gain insights into our data, identifying patterns, and make informed decisions about data pre-processing and modeling. We will be working with the dataset we created in the previous lectures to demonstrate various techniques for data using PySpark. Before we proceed, let's quickly recap the dataset we will be using. It contains information about employees, including their names, age, and salaries. Here is the data we have. We are going to run this. And now we can talk about exploratory data analysis, and we are going to create DF again when we talked about it. Exploratory data analysis involves a series of tasks that help us understand the structure and characteristics of our data. Let's perform some common exploratory data analysis techniques using PySpark. We are going to start by summary statistics. Summary statistics provide a quick overview of the central tendencies and dispersion of our data. Let's go with creating the DF again. Spark create DataFrame, you already know. We are going to give a list like name, age, and salary here, and we are going to run this. Then we are going to import the necessary libraries here, like from PySpark.sql.functions. We are going to import mean and standard deviation here. And let me scroll down a little bit. We are going to say summary stats is going to be equal to the df that describes same as pandas, and we are going to give the column names. Of course, we can use with integers only, and we are going to say summary stats.show like this. In the code example, we calculate summary statistics for the age and salary columns using the describe method. This provides information such as count, mean, standard deviation, minimum and maximum values for each column. Also, I need to say this once again, it only works with integer columns. Now let's do some data visualization. Data visualization is a powerful technique to understand data patterns visually. We will use the Matplotlib and Pandas libraries to visualize our PySpark data frame. Let's start by importing necessary modules for data visualization. We are going to say import matplotlib.pyplot as plt, and we are going to import pandas as pd. We are going to run this, and we are going to say PDDF is going to be equal to the df to pandas. It's this easy to convert. We just converted our PySpark data frame to a pandas data frame for the visualization. Now let's create a scatter plot. We are going to say plt.scatter is going to be equal to the df pddf, and we are going to say age, and we are going to use pddf salary here like this, and we are going to say plt.xlabel is age and plt.ylabel is salary, and let's add a title like plt.title, and it's going to be age versus salary, and use plt.show here. So it's meaningless because we have 3 entries, but think it with a bigger dataset, we are just simplifying everything. Let's create a histogram for seeing the distribution. We are going to use plt.histogram like this, and we are going to say pddf, and we are going to say age. Let's do it for age, and we are going to say bins is going to be equal to 10, and let's set edge cover to black, and we are going to say plt.xlabel is going to be age, plt.ylabel is going to be frequency, and plt.title age distribution, and let's display it like this. In the code example, we convert the PySpark data frame df to a pandas data frame pddf for data visualization. We then create a scatter plot to visualize the relationship between age and salary, and a histogram to observe the distribution of ages. Now we are going to talk about correlation analysis. Correlation analysis helps us understand the relationships between different variables. For this, we are going to say correlation matrix is going to be equal to the df stat correlation, and we are going to say age and salary, and we are going to print correlation between age and salary, and we are going to say correlation matrix here. As a quick reminder, correlation takes values between -1 and +1, and it's so close to the +1, which means they have a positive strong relationship, which means that they are going to move together. Like if the age is increasing, salary is also increasing with it. In the code example, we calculate the correlation between age and salary using the correlation method from the DataFrame's stat module. Now we will explore the power of PySpark SQL functions to perform various data transformations and manipulations efficiently. PySpark provides a rich set of built-in SQL functions that allow us to process and analyze data seamlessly. PySpark SQL functions provide a wide array of operations for data transformation and manipulation similar to those found in SQL. Let's dive into some common data transformations and manipulations using PySpark SQL functions. PySpark SQL functions allow us to transform data in various ways to create new columns or modify existing ones. Let's apply arithmetic operations to create a new column. For this, we are going to say from PySpark SQL functions import call, and we are going to say df transformed. Df transformed is going to be df with column increased salary, and let's say we are giving a 10% raise to the salary, and let's use df transformed show like this. In this example, we can see that salary is increased by 10%. We used the with column function to create a new column increase salary in the data frame. We apply an arithmetic operation to increase the salary by 10% for each employee. Now let's use string functions. We are going to say from PySpark.SQL functions import concat, and it like this, and we are going to say df transformed df with column modified name, and it's going to be like concat column name, and let's say let employee, like this, and we are going to run this, and we are going to see. I'm going to capitalize this, and it's not going to raise error. I'm sorry for that. And now we are good to go. Now I'm going to run this with show, and we are going to see that modified name is added, like Alice employee, Bob employee, Kathy employee. Here we use the with column function again to create a new column modified name by concatenating the name column with the string employee. PySpark SQL functions also enable us to manipulate data based on the conditions and perform aggregations. Now we are going to see filtering example. We are going to say df filtered is going to be equal to df.filter and column age, let's say they're greater than 25. And when we run this, we can just check like df filtered show, and in this example, we use the filter function to retain only the rows where the age column is greater than 25. Now let's see an example about aggregating data. We are going to say from PySpark SQL functions import average, and we are going to run this. Let's set the average salary, like we are going to say df.aggregate, and we are going to say average column salary, and we are going to use .collect here, and we are going to add 2 of this, and we are just going to run this like this. Now we are going to say print average salary, and we can print the average salary like this. In this example, we use the aggregate function along with the average to calculate the average salary for all employees. Now we will explore how to aggregate and summarize data using PySpark's group by and window operations. These powerful techniques allow us to analyze data at various levels of granularity and perform advanced calculations. We are going to use the same dataset we created earlier. Aggregating and summarizing data are essential tasks in data analysis. PySpark provides two powerful methods to accomplish this: group by and window operations. The group by operation allows us to group data based on one or more columns and perform aggregations on each group. Let's start with the example 1, grouping and aggregating data. Let's import necessary modules. We already imported that, but I'm going to import the necessary ones in every lecture for getting used to syntax of the PySpark. We imported average and max from PySpark SQL functions, and we are going to run this. Let's group the data by age and calculate the average and maximum salary for each age group. For this, we are going to say grouped data is going to be equal to df group by age, and we are going to use aggregate average salary, and we are going to use maximum salary like this, and we are just going to run this, and we are going to say grouped data show. In this example, we use the group by method to group the data by the age column. Then we use the aggregate method along with average and maximum functions to calculate the average and maximum salary for each age group. The window operation allows us to perform calculations across a window of data, such as moving averages or cumulative sums. For an example of window operations, we are going to import from PySpark.sql.window import window, and from PySpark SQL functions import sum. We are going to define a window specification like window spec is going to be equal to the window.order by and age. Let's calculate the cumulative summary of salaries based on the age ordering. For this, we are going to say df with cumulative summary, df with column cumulative salary, and we are going to say sum salary. We are going to use over window spec, and we are going to use show on that, df with cumulative summary show. You can see that we got some errors, but we have the cumulative summary here. It worked nicely. Also, you can see that the data is ordered by the age column. Here we use the window class to define a window specification based on the age ordering. We then use the with column method to create a new column, cumulative salary, containing the cumulative sum of salaries within specified window. Now we will explore how to leverage user-defined functions to perform custom data transformations and computations in PySpark. User-defined functions allows us to extend PySpark's functionality and tailor data processing to specific requirements. We are going to use the same dataset for this lecture also. PySpark allows us to define custom functions using Python and apply them to DataFrame columns to perform specific operations. For example, let's define a simple user-defined functions to add a prefix to the name column. So we can say define add prefix, and let's pass name inside, return Mr. and name. Now we are going to import from PySpark.sql functions, import user-defined function, and from PySpark SQL types, import string type. We are going to run this, and we are going to say add prefix user-defined function is going to be equal to the user-defined function add prefix, and we are going to pass string type here. Now we are going to apply the user-defined function to the name column, like we are going to say df with prefix is going to be equal to the df with column and prefixed, let's say name, and we are going to say add prefix user-defined function name, and we are going to run this. The error is caused because of the capitalization here. We are going to run like this, and without a typo it works, and we are going to use df with prefix.show. For seeing the new version, we can see that prefixed name here. In this example, we define a simple user-defined function add prefix to add the prefix Mr. to the name column. We register the user-defined function using the udf function and specify the return type. Then we use the with column method to apply the user-defined function to the name column and create a new column prefixed name with the modified names. Now let's see another example. We are going to see using user-defined functions with multiple columns. For this, we are going to define a function as calculate total income, and we are going to pass age and salary into it. We are going to say return age and salary. It's kind of meaningless, but let's do this for showing you how it works. PySpark SQL types, we are going to import integer type. We are going to say calculate total income UDF. UDF is going to be equal to the calculate total income, and it's going to be integer. We are going to use like this, and type, and we are going to run this. Now we are going to apply the UDF to calculate the total income. It's not total income, but just treat it like that. df with total income is going to be equal to the df with column. We are going to say total income, let's say doesn't have a meaning. Let's add this also. Maybe some people is watching without sounds, and we are going to say calculate total income user defined function, we are going to say age and salary here. And let's get back to the starting of this cell, and we are going to say def with total income dot show. Here we define a UDF, calculate total income, that calculates the total income based on age and salary. We register the user defined function with PySpark, specifying the return type as integer type. We then use with column method to apply the user defined function to the age and salary columns and create a new column total income, and we added doesn't have a meaning with the calculated values. We are going to start to the machine learning section in the next part. I'm not going to make any type of introduction to concepts or similar things like that. I'm just going to show you the PySpark syntax for you to use linear and logistic regression and evaluation methods, and that's going to be all about the machine learning part of this course. Machine learning is a type of artificial intelligence that allows software applications to become more accurate in predicting outcomes without being explicitly programmed to do so. Machine learning algorithms use historical data as input to predict new output values. It's not always historical data, but you're basically predicting a feature based on other features. We are going to start with supervised learning algorithms, part of the machine learning. Supervised learning algorithms, which are widely used for tasks like classification and regression, will work with a new dataset specifically designed for this lecture to illustrate the concepts and demonstrate how PySpark's machine learning library and machine learning packages can be leveraged for these tasks. For this lecture, we will work with a dataset related to house prices. The dataset contains information about various houses, including features such as the number of bedrooms, bathrooms, square footage, and the sale price. We will create the dataset programmatically for demonstration purposes. I'm not going to create all the entries one by one, but I'm going to say Spark is going to be equal to the SparkSession. Remember it, .builder, .app name, and let's say supervised learning, and we are going to use get or create here, and we are going to run this. It says using an existing Spark session, only runtime SQL configurations will take effect. It's not important. Now I'm going to show you the data we are going to work with. I just made a pasting operation. I'm not going to write this with my hands and keyboard because it's going to take too much time, and this is kind of a crash course, so time is important, I think. We are just going to create a schema here for you to understand the structure. Let's start by running this, and we are going to say schema is going to be equal to the struct type. We are going to say, you know how to create data in PySpark. We created it a lot in this lecture or course, both can be said for this video. Struct field, and we are going to use curve fit, and it's going to be float type, and we are going to say true. But one important thing here, we didn't import it float type, so let's keep with importing it from the SQL functions. Import float type. The others we imported, but this one we didn't. Let me just fix the typo there, and it's from the types. I'm sorry for that. We are going to run like this, and now it works smoothly. Let's delete these ones, and we can keep creating our schema here. Like, we are going to use struct field again with bedrooms. We are going to say float type, and we are going to say true. We are going to say struct field bathrooms float type, and we are going to say true. And last one, struct field price, it's also going to be float type, and let's say true to this also. By the way, they're all integers, not floats, but I want to show you the float type also because it's a commonly used thing in PySpark or in any data operation. Now we are going to create our df as Spark create DataFrame data and schema, and we are going to run this. Actually, we got errors because of the float types. I'm just going to fix it, and I'm just going to change them with the integer type, and I'm going to come back in a second. I think now we are good to go. We are going to run this. I just made change on here, and we are going to run this. And as we can see, it works smoothly. Let's use the.show, and we are going to see our data in here. Supervised learning involves training a model on labeled data, where each data point is associated with a target or label. The model learns from the features in the data and the corresponding labels to make predictions on new unseen data. Let's start with classification. We are going to start with classification with logistic regression. In this example, we are going to perform a binary classification task using logistic regression to predict whether a house's price falls within a specific price range, and then we are going to use linear regression also. We are going to start by importing the necessary modules. We are going to say from PySpark.machine learning feature, we are going to import vector assembler from here. From PySpark.machine learning classification, we are going to import logistic regression, and from PySpark.ml, we are going to import pipeline here. Let's run this. Now we are going to create the feature vector. For this, we are going to say feature columns is going to be equal to the square. I need to open a list. I thought I did that, but it didn't apply it. Let's also add this square fit and bedrooms and bathrooms. And we are going to set assembler with vector assembler. We are going to say input columns equals to the feature columns, and output column is going to be equal to the features. And we are going to run this, and we are going to know df assembler is going to be equal to the assembler.transform, and we will pass our data frame inside of it. Now I'm going to show you how you can split your data by train and test data. It's really important in machine learning because you need to evaluate your model's performance on test data. With training data, you are going to make some predictions and you are going to test if they are accurate on the test data. Because of this splitting is really important. In a small scale data like this, as you can see here, it's not important. Also, our model is not going to be that accurate, but in a larger data sets, you need to evaluate your model's performance. For this task, we can use we can say train data and test data is going to be equal to df assembler that random split we have here, and we are just setting the test and training size. The first one is the training size. Using 0.8 means 80% of the data is going to be it's going to be in the training data, and we are going to say 0.2 for the test data, and we are going to run it like this. Now we are going to train our logistic regression model like logistic regression. Use logistic regression features column is going to be equal to the features, and label column is going to be equal to the price, and let's say model going to be logistic regression.fit, and we are going to say train data here. We made a typo there. I'm quickly going to fix that and run the cell. And this is the logistic regression model we have here. It's trained on 17 seconds. And let's make predictions. We are going to say predictions is going to be equal to the model.transform test data, and we are going to say predictions select features price and prediction. Actually, logistic regression is not the best algorithm for this task. Linear regression is better because we are predicting a continuous variable, like the prediction value here needs to be 1 or 0 for it to be binary. I just wanted to show you all this because I just wanted to show you how you can train a logistic regression model in PySpark, but predicting a 0 and a 1 value like a binary result is going to be okay for logistic regression. Actually, logistic regression is a classification algorithm and we are not doing any kind of classification here. Because of that, it also raised an error like this. It is not a good way to forecast or make predictions. The better one, like if your data is like the labels are like 1 and 0, like the customer is going to buy the data and it's 1, and if the customer isn't going to buy, then it's 0. You can use a logistic regression and it's going to be nice on that, but in this case it's not a useful method. The linear regression would be super good for this task. Now we are going to apply linear regression, the true way to predict this value. Let's import linear regression from PySpark machine learning regression. Import linear regression. And we are going to say linear regression is going to be equal to the linear regression, and features column is going to be equal to the features, and label column is going to be equal to the price, and we are going to say model equals to the linear regression fit train data, and we are going to set predictions is going to be equal to the model transform test data, and we are going to use predictions dot select features. Let's write the same price and prediction here, and we are going to say that show. And here is our result. You can see there is no errors because we are using a true type of algorithm. If you are predicting continuous variables, using regression is the best option. In this supervised learning algorithms, classification and regression lecture, we explored supervised learning algorithms using PySpark machine learning library and machine learning packages. Don't forget, if you have a binary label like 1 and 0, use logistic regression. But if you have continuous values in your label, like this is the value you have in your label, use regression. In this lecture, we worked with a dataset related to house prices and performed classification using logistic regression, which wasn't the best way, true way, and regression using linear regression. Supervised learning is a fundamental concept in machine learning and is widely used for various predictive tasks. Now we will explore unsupervised learning algorithms, which are used to identify patterns and relationships in data without labeled target variables. We will work with a new dataset specifically designed for this lecture to illustrate the concepts and demonstrate how PySpark's machine learning library and machine learning packages can be leveraged for these tasks. For this lecture, we will work with a dataset related to customer segmentation. The dataset contains information about customers, including their spending behavior on different product categories. We will create the dataset parametrically for demonstration purposes. For this dataset creation process, we can also create a SparkSession, like we can use SparkSession, but it's not necessary and it's not going to change anything, so I'm not going to use that. I'm just going to paste the related data here like this. This is the data that I'm going to use in this lecture, and I'm just going to run this data. And now we are going to create the schema together. Schema is going to be equal to the struct type, struct field. We are going to say customer ID, it's going to be string type, and it's going to be true. And we are going to say struct field spending electronics, it's going to be integer type, and true. We are going to say struct field spending fashion, it's going to be integer type, and true here. And the last one, struct field spending grocery, it's going to be integer type, and true again. There is something wrong because we can see from the colors like this. Let me quickly fix this. We need to add this into here, and now we can create our schema like this. Now we are going to use df spark create DataFrame data and schema like this. I'm going to fix the typo and it's going to be cool, I guess. Let's display the data frame we have. We are going to use df show, and we can see our data frame here. Then we can talk about unsupervised learning. Unsupervised learning algorithms aim to discover patterns and structures in data without using any labeled target variable. Remember the label we have. I'm saying label, but let me show you. The price is the label in this data. Like we are trying to predict the price, so it's the label. But in the new data we created, there's no such thing as label. Think it as grouping. Two common unsupervised learning tasks are clustering and dimensionality reduction. We are going to talk about one of them. We are going to start with clustering with the most popular algorithm, k-means. In this example, we will perform customer segmentation using the k-means clustering algorithm to group customers based on their spending behavior. It's type of distance-based algorithm, but I'm not going to talk about algorithm. I'm just going to show the syntax of it. We are going to import k-means from PySpark.machineLearning.clustering, import k-means, and we are going to run this. We are going to create the feature vector using vector assembler, but I'm not going to import it again. Let's use feature columns, and we are going to say spending electronics, spending fashion, and spending grocery. We are going to run like this. We are going to set assembler, and we are going to say vector assembler input columns is going to be equal to the feature columns, and output column is going to be equal to the features. We are going to say df assembled is going to be equal to the assembler dot transform data frame. Let's train the k-means model. Like k-means is going to be equal to the k-means. We are going to say features column is going to be equal to the features, and k, I'm not going to say what it is, but it's think it like neighbors, grouping neighbors, and we are going to run like this. We are going to say model is going to be equal to the k-means dot fit df assembled, and we are going to run this. Now we are going to make predictions also, and we are going to say model dot transform df assembled. We are going to run like this. Also, you are going to remember that we had train and test data in the supervised learning, but it's unnecessary since there is no labels on. We can't evaluate the model's performance because we don't have labels in this. Let's display the predictions we made. We are going to say predictions.select customer ID features prediction, and we are going to say show here like this. And you can see that we grouped customers based on their purchasing behaviors. Like they have groups like 2, 1, 0, and we can give decisions on this information. Like let's think about it. Let's brainstorm about this. If the Customers with the group 2 is purchasing more electrics and more likely to purchase on that category. We can just show more ads to them in the necessary field. Now we are going to talk about dimensionality reduction with principal component analysis. We will reduce the dimensionality of the data using principal component analysis to identify the most important features. For this, we are going to say from PySpark machine learning feature import principal component analysis. In a small dataset like this with 8 entries, it's really unnecessary, but I'm just showing you the syntax of it. We are going to say PCA is going to be equal to the PCA, K is going to be 2, input column is going to be equal to the features, and output column is going to be equal to the PCA features. And let's run this firstly. We are going to say model is going to be equal to the PCA fit df assembled. We are going to say df PCA is going to be equal to the model.transform df assembled. We are going to run like this. Let's display the PCA transform data. For this, we are going to say df PCA.select, and we are going to say customer ID and principal component analysis features, and we are going to say that show and truncate is going to be equal to the false. Let's run this, and we can see our principal component analysis features. In this unsupervised learning algorithms lecture, we explored unsupervised learning algorithms using PySpark machine learning library and machine learning packages. We performed customer segmentation using k-means clustering and reduced the dimensionality of the data using principal component analysis. Unsupervised learning is a powerful technique for finding hidden structures in data without relying on labeled target variables. That was all for the PySpark course. Thanks for watching. I create content about data science and programming. If you are interested in these topics and want to see more content like this, you can subscribe to my channel. I also have courses about Excel, Python libraries, Powers, which is another great big data handling library written in Rust. Also, I have courses about data visualization like Plotly course, Matplotlib course. If you are interested in data science or data related topics, you are going to find good videos on my channel, I think. Thanks for watching this course. I hope you enjoyed it and I hope you found it informative. Have a great day.